When a laser emits beams of light, particles called photons, at a screen with two slits, you'd expect to see two strips to correspond with the two slits. Instead, we see a pattern of light and dark bands. This suggests that light behaves like waves that pass through both slits simultaneously, interfering with each other to create the pattern on the second screen. However, when scientists used a measuring device to observe the slit that each photon passed through, the interference pattern disappeared and two strips appeared. The act of observing which slit it went through changed the behavior of the photons. This happens because a photon isn't really taking one path or the other. It exists as a combination of both possibilities at once, one for each slit. When you add these two possibilities together and calculate the probability of where the photon lands, an extra term appears that exists only because you're combining the two waves. This is the interference term, and it's what creates the alternating bright and dark bands. But the moment a detector measures which slit the photon went through, the photon becomes entangled with the detector, and this interference term disappears completely from the math. What's left is simply the sum of the two individual probabilities, with no interference between them, which is why measuring the photon makes the interference pattern disappear, leaving behind two ordinary strips instead of many bright and dark bands.